Welcome to the Explainer. So, look, if you've ever built a semantic search feature, you probably know that doing the initial data dump is actually pretty easy. But keeping that AI evidence perfectly aligned with reality in a production environment, yeah, that's usually where things completely break down. Today, we're going to fix that. We're building a robust, secure, and continuous live synchronization pipeline between your source data and your AI vector stores. Think of this as your absolute architectural blueprint for surviving production.
All right, let's just quickly look at the agenda for today. We'll be going through 6 parts. 1. Beyond the Stale AI demo. 2. Securing the live sync. 3. Stable identity for AI evidence. 4. Handling consistency and recovery. 5. Avoiding architecture anti-patterns. And 6. Preparing for deterministic RAG. We are completely shattering the illusion that one-time data backfills are ever enough. Let's jump in.
Section 1. Beyond the Stale AI demo. Let's expose the 2 distinct time horizons of AI integration. Adding semantic search to an existing app always exposes 2 totally different phases. First up, you have the initial backfill. This is all about establishing your derived historical evidence from existing database rows. But the second horizon, that's live data sync. A backfill makes for a really great demo, but honestly, that demo becomes completely stale the literal microsecond a real user modifies the database. If you aren't handling continuous trusted creates, updates, and deletes, your AI is essentially just generating answers based on an out-of-date reality. AI Fabric explicitly separates these 2 concerns.
Now, looking at this initial backfill workflow, you'll see it is never just blindly dumping data over the fence. To properly finish the job, you have to follow the steps. Step 1, scan the existing rows. Step 2, enqueue the finished items. Step 3, drain that queue completely. And step 4, this one is absolutely crucial. Verify that the expected vectors are actually retrievable. If you skip that and can't verify the vectors at the end, well, your migration just isn't actually complete.
Moving right along to Section 2, Securing the Live Sync. We need to look at how we protect the boundary between the browser and the backend.
The crucial takeaway here is understanding exactly who is responsible for what. The browser is only allowed to supply the article content and its intent, like does it want to create, update, or delete. That's it. The browser should absolutely never supply a trusted tenant, off-context, or vector space. Why does this matter so much? Because the backend has to derive all of those values itself from a verified identity and persisted source state. Now, the system does have a bypass, but it's strictly opt-in and is only injected by the backend. The access policy keeps everything locked down to exact upsert and delete scopes. I absolutely love this rule. A front end cannot prove trust by sending system-shaped JSON. It just perfectly hits the nail on the head. Anyone can craft a JSON payload that looks official, right? This single principle is exactly why AI Fabric requires a verified off-context and delegates directly to the entity access policy. It stops malicious actors dead in their tracks.
All right, Section 3, Stable Identity for AI Evidence. Here's how we keep our derived data perfectly aligned with our application's truth.
As you can see in this breakdown, there is a right way and a very, very wrong way to handle IDs. The correct architecture uses the source article ID as the whole record logical ID. So when an update happens, you upsert that exact same ID, which seamlessly replaces the old text. Deletions target that exact ID, making them completely reliable. But look at the incorrect architecture. Generating random vector IDs or chunk IDs for whole record updates? No way. If you do that, updates just leave stale versions floating around, and deletions become wildly unreliable, leaving you with orphan data.
And, identity isn't just about the ID itself, it's about the shape of the data. Your normalizer has to project only approved fields. Things like internal notes, they never sync. It bounds the content lengths to protect privacy, and, most importantly, it explicitly fails closed on invalid or oversized input rather than just inventing fake evidence. Embedding and vector failures must remain explicit because we definitely don't want our AI hallucinating what it thinks should have been synchronized.
Which brings us to Section 4, Handling Consistency and Recovery. Time to deal with the nightmare scenarios of distributed systems.
Okay, here's the ultimate architecture test for you. What happens when a database commit fails after a vector write? Throwing an exception on an upsert failure can roll back your local database transaction, sure, but remember, a relational database and a completely external vector provider do not share an atomic transaction. So a response might get lost in transit after a write, or the source commit might just randomly fail afterward.
Because responses can be lost so easily, These rescue mechanisms are literally non-negotiable. You absolutely need stable, logical IDs, correlation traces for debugging, and impotent retries. Plus, you need an explicit reconciliation endpoint that reloads source rows and explicitly reports every single result. And if a batch is oversized, reject it before any side effects happen. These tools ensure that a failed operation doesn't just masquerade as a generic success.
Let's pivot to Section 5, Avoiding Architecture Anti-Patterns. Let's study the traps that destroy production systems.
These are the classic traps developers fall into when they're rushing to get to production. Anti-Pattern 1, publishing the raw DataSync controller directly to the front end. Anti-Pattern 2, letting the browser dictate the tenant and auth context fields. If you do this, you are explicitly permitting identity forgery. The system will just trust whoever knocks on the door. And Anti-Pattern 3, which we touched on before, generating random vector IDs for every update. The result of all these shortcuts? A completely broken system filled with identity forgery and impossible deletions.
Look at this comparison here. Bad architecture hides failures behind generic green success cards. No fallbacks should ever invent evidence, and no success card should hide a failure. But in AI Fabric, if one row works but another exceeds normalization limits, explicitly reporting an invalid underscore request for that specific row is a feature, not a bug. The good source rows remain unchanged, and this visibility lets operators identify the exact failed ID, fix it, and retry it without having to roll back perfectly good data.
Finally, Section 6, Preparing for Deterministic RAG. Let's bridge this architecture into your next lab environment. So, in the Prod 05 lab, you aren't just going to be theorizing about this stuff. You'll be getting your hands dirty, physically implementing it. You're going to build this trusted boundary, prove out your stable CRUD behavior, and deny raw access. And crucially, you will exercise these exact reconciliation failures using local ONX and Lucene to simulate external providers. You are literally building the safety net that prevents disasters.
Because ultimately, all of this sets you up for Prod 06, turning everything we've built into a deterministic RAG quality gate. So I want to leave you with this final thought as you build out these pipelines. Is your resulting AI evidence a deterministic quality gate, or is it just a guess? When your pipeline inevitably breaks, does your architecture guarantee the truth, or will it simply invent evidence? Build the sync right, and your AI will always speak the truth. Thanks so much for joining me on this explainer, and I'll see you in the next one.